This is the higher paper for Year 10 Triple, and it was the sample assessment material released just before the exam. So this is a higher paper. There's your higher calculations for your triple. And the first question kicks off with a nice meaty literacy one. So they'll probably always do this first question, try and tie you up. We've got a bunch of information telling us about a low carbon revolution. And then we've got energy sources in Wales. This is from Wales only, and that's worth noting. And then we're given a little bit about how it generated in 2011 28,000. But there's the proposal of this new station with the potential to generate that much. So I've highlighted that because as I've gone through and answered the questions, these are the bits that's important. So the first question is about discussing what the term means about this low carbon revolution. And you're always going to get kind of a question like this where if we use less fossil fuels to generate electricity, there's going to be less CO2 produced. So there's going to be less global warming. Now, this is for 2 marks, sometimes worth 3 marks. But in every paper, they've got something that discusses the effect of, fossil fuels on the environment. And then it refers to figure 1. To identify trends in different energy sources between 2009 and 2011. So when I go up, I'm just going to do 2009 to 2011. And I can see that there's a slight decrease in gas there, but everything else remains pretty similar. So, and that's what I've said. So there's a reduction in gas used to generate electrical energy, but the other energy remains similar. So it's saying that Wales actually used 45,000 gigawatt hours of electric energy. But when we look, we only produced, 28,000. So how are we going to get that energy? And this is kind of a national grid question where we'll say that because the national grid connects users to power stations via a network of cable and transformers, that's pretty much your definition for the national grid there, that we can source that energy if we need more. So that's a huge benefit of having the national grid. And then it says, if this station, Wilfer B, had been commissioned, what's the surplus? How much leftover electricity or energy would we have? Because we needed this much. We only produced this much. But this station can give us an extra 23,000. So what I've done, I've added that extra 23,000 to what we generated in 2011. That gives us 51,000. Well, we only used 45,000, so the surplus energy was 6,000 gigawatt hours. All right. And then figure 2, this is figure 2. So it's just showing now from renewable sources. And you can see I've got a big circle around solar panels there because which energy didn't make it, and you can see that there's no shaded boxes there, so there's no information from solar panels for 1 mark. And then this question, for the period considered 2004 to 2011, the wind changes, explain why this. So wind shows a significant increase in 2011, whereas the others are pretty constant. So when we have a look at wind speed, this is your wind. Not wind speed, I shouldn't say, the wind, energy produced by wind. You can see there's a significant increase there. So that's the answer to that. That's why I explain why renewable energy was mainly responsible for this, because of the wind. And then figure 2, how would it look if you included the solar cells? Well, the bars are going to be taller as more electricity is generated by renewable sources. So they're saying if we did include this information, every bar would be a little bit taller. Okay, so that's question 1 there. So question 2 is a triple question. So explain clearly how you'd use Fleming's left-hand rule. So I've tried to take a photo, and I mean, this is always going to be difficult, but what you've got to remember is that your first finger, so it's telling you that it flows from W to Z. And the magnetic field is always going to be north to south. So your first finger has got to be going from north to south. That's what I've tried to represent there. And then it's going from Z to Y. So Z to Y is your second finger. Therefore, your thumb is going to be that upward force. Sorry, I had to think then. So it was Y to Z, actually. So it's Y to Z. So your second finger is going to be, yeah, I've written it wrong there, current Z to Y. It should be Y to Z. So I've written that wrong. So, but this is right now because my finger is coming out this way with that direction. It's really hard to show on a video, but that's what, for 3 marks, you try and identify every finger there. How can you change the coil to move in the opposite direction? You just reverse a battery. That's all you do. And then what changes can you make to make the coil turn faster or rotate faster? You can use a stronger magnet, you can use more coils, you can use a larger current, or you can add an iron core to that. And I think that is that question there. Okay? Which brings us on to question 3. So question 3 is fairly straightforward so long as you understand the concept of parallel and series circuits. Because when this is open, and I know we've got, we usually have the power up this end and then either the bulbs or the resistors down this end, but if you turn this around, then you've got that. It doesn't matter where you put the power supply, really. They're just trying to confuse you. But if this is open, then there's no current flowing along here. So you literally got a series circuit there with a voltage of 230 and a resistance of 40. So knowing that now, we should be able to calculate the current using I equals V over R. So there's no rearranging required there. That's the equation you're given in the front. And that's going to be your voltage over your resistance here. Okay? And that gives you 5.75. I think really nice question there for 3 marks. And still a nice question as you come on to the power now. So now that you know your current, you can use power equals voltage times current. Your voltage is going to stay the same. And you've got that current there. And again, 3 marks. So there's a possible 6 marks here for something that's quite achievable. It does get a little bit tricky, though, for the next question, because when you close that switch, it means now you put another component in parallel. And adding components in parallel reduces the overall resistance of the circuit. So this in turn is going to increase the power. So if you decrease current, you're going to increase, if you decrease resistance, you're going to increase current. So if you increase current, you've got to increase whatever's on this side. If your voltage remains the same, so if we say a voltage is 230 and your current, let's just say it's 1. If you increase current to 2 times 230 is going to give you a higher value this end. So you've got to increase it. And in fact, I think it doubles because they are the same resistance. So you're going to actually double the power. You're going to double the current by half in the resistance. That's what happens when you add components in parallel. If you'd add it in series, however, then you're going to add more resistance, which means you decrease the current there. And then this is probably going to be the last question for this part, and then I'll do a part 2 then with the rest of the questions. So a satellite question kind of wrapped up with a little bit of numeracy for a 6 marker here. I'm just going to identify some numbers. So we got 9 kilometers is the distance here of this fiber optic cable. And it says that the information along this optical fiber travels at half the speed as an electromagnetic wave. Now, electromagnetic waves move at the speed of light. That's 3 times 10 to the power 8. But we don't need to know that because what we can do is work this into a numeracy sort of problem. It's telling you the distance there to the satellite, but remember now that you're going to need to times that by 2 because it needs to come back down as well. So if we're going to be calculating speeds, which we will be, then we're going to have a look. So a top secret message needs to be sent. So which one are we going to send it by? We're going to send it the short distance, which is, but the signal travels half the speed, or we're going to send it long distance at double the speed. Well, I've said using microwaves for geostationary satellites means a longer distance to travel, but they do travel twice as fast. Okay, and when we look at that, so I've got that 36,000. We're going to times that by 2 because it's there and back. And we're going to see then how many times that 9,000 goes into it. Now we can see that the satellite is 8 times the distance of this fiber optic cable. So it's 8 times the distance of this. So which one's better? Let's have a look. Well, I've said infrared signals travel at half the speed, so it will still be a quarter of the time to transfer the information via optical fibers. And they also have more security and a very low error rate compared with microwaves. So I'm going to choose the optical fiber. So in other words, it's going to get there quicker. It's going to get there a quarter of the time, because even though it's half the speed, it's still twice as fast. So that gives you a quarter of the time. And if you send it through satellites, there's a chance then for microwaves to get hacked. And if it's what do they call it, a high security or an urgent message, top secret, then we want to have the best security. And the best security with the lowest error rate is going to be your microwaves underground in the optical fiber. A geostationary satellite is a special type of satellite. Now, geostationary, they've made mistakes with this before, where they've actually had geosynchronous as this definition, but since they've amended it, and we need to know that geostationary is the one that stays at the same point above the Earth. Now, I've tried to do this. There is a good video on this, an OMG video where I show you. But if it's geostationary, it's going to orbit around the equator. So if the Earth is spinning, and it takes 24 hours to spin, so does the satellite, which means it stays in exactly the same spot. So if you was to put a satellite above Cantonian High School, it's going to stay there above Cantonian High School. It's just going to be stationary, geostationary. Whereas a geosynchronous, if the Earth is spinning this way, then this might take an orbit there. So it's never going to be at the same spot until 24 hours later. So you can only communicate with a geosynchronous satellite every 24 hours. So my answer to this is the orbit above the equator, orbit period of 24 hours, but it does stay the same because it's the same direction as the Earth spin. Okay? And I think I'm going to leave it there for this video and then come back with part 2 of this paper.